Okay, this video is going to be called Ion Pumps for Medical Students, Understanding Ion Pumps for Medical Students. If anybody's not a medical student, you might be bored. I'm going to go through some technical stuff, but if you want to learn, you don't have to be a medical student. If anybody's interested in understanding ion pumps, which are very useful to understand for understanding hypertension, for understanding neurophysiology, for understanding cardiac physiology, the emphasis today is going to be on cardiac physiology, the action potential of a cardiac ventricular cardiomyocyte muscle cell, okay? And the reason I'm doing it the way I'm doing it here is to show you like a philosophical system of understanding stuff. I'm going to show you a little bit about my background just so you know where I'm coming from, because I was a phenomenal student, and I'm showing you that my way of understanding this and teaching it is much better than anything you're going to see in any of the medical schools. Okay, I graduated first in my med school class, first out of 333 students. I wrote this book, Med Students Guide to Top Board Scores. The dean of my medical school, Dr. Wallace, wrote the foreword. I ended up writing a bunch of other stuff about study skills. Straight A at Stanford, on to Harvard. I got 99% on my residency boards as well. And it wasn't like I just had that high an IQ. I had really good study skills. I wrote some other books about study skills and how to increase IQ, how to raise IQ and become a genius, Underground Guide to Study Skills, etc. I've written a bunch of medical books as well. Here's a book I wrote back with Amersis Elsevier. I also did fellowships. I did fellowship in interventional radiology at Harvard, and then I also did a fellowship. And I wrote a textbook of interventional radiology procedures here. That's me when I was young, in my 30s. I went through a fat phase for a couple of years. Lost all the weight over 20 years ago, many years ago. I wrote this textbook of interventional radiology, translated into Spanish, etc. That was with Amersis Elsevier Publishing Company. I wrote other stuff at Little Brown and other publishing companies, and I self-published a lot of books. Okay, now I'm going to start showing you my system. Well, actually, let me show you a few other things. Here was my diagnostic radiology boards book, and what I did was I took this book in outline format, put tons of note in the margins here. Let me give you a bigger picture so you can see it better. And what I wanted to do is have everything in one spot so I could always find the information. I was done like in an hour, 10 minutes of a 4.5-hour test with a perfect score. So anyways, I had everything in one spot. I used this book so much, it's dog-eared, I had to retape it. I would put mnemonics and other little extra information in the back wherever I could fit it in. It comes with an index. It's always nice to have an index because you can find stuff fast. Back when I was a resident, we didn't even have the internet. And I'd write in the margins all over the place. The point of this was everything's in one place. A lot of people like Anki flashcards and stuff like that, but you run the risk of them being deleted or you losing access to them. Again, all these notes in here are outline format, so I could find everything real fast. And I knew where every single thing was, okay? Then for my oral boards after my neuroradiology fellowship, I'll just show you the book. See, I got tabbed indices. I just took this book that was really not that great of a book, and I taped a bunch of pictures into it. Again, why do I do all these? These are condensed notes. So this would be standard, outline format condensed notes. This would be, I call this illustrated condensed notes. I would tape pictures from journal articles in here and from other textbooks to get everything into one spot so I could always find everything very quickly. They told me, this is not official, they told me I'd gotten a perfect score on my oral boards as well. But anyways, this is how I did it. And the secret was, a lot of people, they freak out the last couple months before boards and try to study. They don't have good material. But I started right from the beginning, always having all my information in one spot, because I had a bad experience when I was in college where I had to move and I lost some books and I was pissed off about that. So I vowed to myself, I will always stay well organized. And every first class I take, I consider that preparation for my final exam. So I keep all my material organized. I go through the question books each time. So I never did an all-nighter in my life, okay? All right, so anyways, I'm giving you that as a background, okay? And then there's other advantage. What I try to do when I encounter a complex topic is to conceptualize it into some big philosophical meaning. And also, by the way, having a good attitude about school just makes you a better student. Like I had the attitude, biochemistry is the language of God that he uses to write the book of life, and therefore if I want to be a good doctor, a good scientist, I have to know it. And that type of attitude made me very enthusiastic to learn biochemistry. And the other thing too is when I was trying to become a doctor, I wasn't just saying, I hope I pass my test and graduate. No, I say I want to be one of the best doctors in the world. I want to discover new things. I want to be as great of a doctor as I could be. And that attitude made me take up more information. Whenever I rotate through something, whatever it was, pediatrics, I'll say maybe I'll be a pediatrician. Surgery, maybe I'll be a surgeon. Whatever it was, I would say maybe I'll do that for a career, because that makes your brain remember more. If you tell your brain something's important, your brain's designed to remember what you think is important. Okay? So get yourself revved up and psyched up to think it's important, and you'll just absorb the material faster, and it's a lot more fun that way. Okay, so when God designed the earth, that's the other thing too, is atheism is stupid, it's for losers. Almost all the best creative people have been religious, okay? You'll see that if you study the history of geniuses. All right, so I'm going to use paintings and all kinds of metaphors, all kinds of things that are not allowed in a regular school, and it's going to make this a lot more interesting, you will see. Okay, so God designed the earth and he created life, and it appears that he created life starting in the ocean, okay? And so here's a key point. In the ocean, you've got salt water, so there's tons of sodium in the ocean water. You've also got these rocks, calcium carbonate, and the water hits against the rocks and it rinses the calcium into the water. So seawater is going to be very high in sodium and very high in calcium. You need to know that because that's the extracellular space. You have to know that. Salt water, seawater, high in sodium, rinsing over the calcium carbonate rocks, the limestone, producing a lot of calcium in the water. That is the extracellular space of the human body. So the first cell, let's say you have a walled-off membrane around the salt water. You can't do anything as long as you've got salt water inside of your cell. You have to pump it out. You have to pump out the calcium. You have to pump out the sodium in order that you can have other things inside of your cell so it may live. All right, so you have to do that for osmotic reasons. Otherwise, you won't be allowed to have anything in the cell. Otherwise, it would swell up. I like this painting by Thomas Kincaid called Clearing Storms, and because you see the waves washing against the rocks, the limestone, and they're going to rinse the calcium into the water. And it reminds me of the quote of Marcus Aurelius, "A man should be like a cliff. All day long the waves beat against his feet, his ankles, but the cliff is not moved." So you're going to just have to deal with stuff. Don't take it personally. Don't get emotional about it. But again, this is putting a lot of calcium into the water. The extracellular space concentration of water, of calcium, is like 10,000 to 15,000 times higher than it is intracellular. And you can't, like I said, you have to get this stuff out, otherwise you can't have life. So what the cell does is it pumps out the calcium and it pumps out the sodium, and then it can take other things inside, make its proteins. It can have potassium in there and magnesium. Okay, so here's the concentrations, extracellular space versus intracellular space. Trust me, everything I'm telling you is real useful. This is going to be useful to you for the rest of your career for understanding tons of stuff about the heart and about the brain, about the muscles, about blood pressure, about a lot of things. So these are ion gradients or ion concentrations in millimoles. So the extracellular space is pretty much the same for the blood and outside of cells. Extracellular space, extracellular matrix, you can call it. So sodium is going to be about 140 in the blood, extracellular, and it's about 10 cytoplasm. So the ratio is about 14 to 1, much higher outside the cell. Like we said, the seawater, the salt water, think of your bodily fluids as being like salt water, all right? Calcium is also going to be much higher extracellular because it's the extracellular space. It's the water. It's going to be, let's say, 1 millimole about, but inside the cytoplasm, it's only 1 nanomole. So it's about 10,000 times higher in the extracellular space and inside the cell. So again, outside the cell is seawater, okay? And the cell does not want to be like seawater. It wants to keep that out, keep the calcium out, keep the sodium out. Potassium is the opposite. When God decided life was going to be created, he put a bunch of potassium in the cell. This is also why when you eat whole plant foods with the cells intact of the plant food, you get a lot more potassium versus a processed food where they grind everything up. They push the potassium out of the cell. You don't want that. Okay, so anyways, the key point is salt water, seawater, high in sodium, high in calcium. And then the cytoplasm is the opposite. It's high in potassium. It's got a ratio of about 35 to 1. Okay? And the relevance of knowing these gradients is the cells always want to, the ions want to equilibrate their gradient. So they're going to flow in the direction of their gradient, all other things being equal. This means that sodium wants to get into the cell big time. It's got a 14 to 1 concentration gradient, so it totally wants to get into the cell. The inside of a cell has a negative resting membrane potential, so that's another reason sodium wants to get into the cell. And I've gave these ions personality. The personality of sodium, it's the angry poor trying to bust in, okay, bust into the city. Calcium is the aristocrat. I'll explain why in a moment. And potassium is the good middle class. It'll all make sense in a moment. Okay, inside a cell, you've got this potassium sodium ATPase. Okay, so it's an ATP pump. That means it's active transport, primary active transport, and it pumps 2 potassium into the cell, 3 sodium pumped out of the cell. This is a positive charge, this is a positive charge. So you're pumping more positives out. 3 positives out, 2 positives in. So the net effect is to pump sodium out. It's basically like an electrical battery. This is an electrical generator, this little pump here. Because you're pumping a current, a net positive charged current pumped out. You're separating charge across the membrane, okay? And that ion flow is the current, all right? So you have a negative resting membrane potential. In a neuron, you know, one of your brain cells, about negative 65 millivolts. But in a cardiac, like ventricular muscle cell, it's a negative 90 millivolts. And we're going to get into cardiac stuff in just a moment. You also have something called a NACA exchanger. Na means natrium, Latin for sodium. Ca is calcium. And the NACA exchanger means you've produced this gradient through your sodium-potassium pump here. And then you can harvest the gradient by allowing sodium to come into the cell and couple that to pumping calcium outside the cell. This NACA exchanger is super fast. It can pump out like 5,000 calciums in 1 second. Okay. Notice that you have to have magnesium whenever you have an ATP reaction because it hangs on to the phosphates and keeps the second and the third phosphate from breaking apart prematurely. So they don't break apart until the enzyme, the pump is ready for them to do so. Okay. Primary active transport, and this is coupled to this gradient, so this is secondary active transport. Okay, now here's a key point. Almost all of the ions that are positively charged inside the cell are sodium and potassium. They account for about 98% of the ions inside your cell, and it's mostly potassium. So what that means is this is always constant. It cannot change. This is inviolate. This is, you know, 10 Commandments written by God. And what this means is you can't have more of these ions in here or the cell would burst because the water is going to follow the osmotic gradient. So you always have to maintain these osmotic gradients. Otherwise, water would rush into the cell and the whole thing would pop. So because of that, it has to be the way it is. I'm letting you know that this stuff is, it's just the way it is. I explained to you why the outside extracellular space has high sodium and it has high calcium. You need to know that, and you need to know that you can't change this. When we get into hypertension, that'll be a separate lecture. It'll explain why high sodium diets cause hypertension because they disrupt the natural ion gradients, okay? But you need to know that you can't change this, that there's always going to be that same net amount for ionic purposes, okay? Because that'll make sense for why the cell does what it does. Okay, now we got to talk about the personalities of the ions. Okay, the first ion we're going to talk about, its personality, is calcium. Calcium is the aristocrat, okay? And calcium is like an aristocrat wife, like Big Mama, okay? In the family, even though the husband, like this guy's pretty nicely dressed, he might be a big shot at work, but in the house, Mama is the boss, okay? Mama bosses everyone around. Mama is the queen aristocrat, just like the queen in chess is the most powerful piece. Everybody knows Mama. Mama plans all the events. Mama invites all the guests. She knows all the guests. The husband is just a chump who pays the bills. Okay, so Mama is in charge. And what this means in cells is calcium, when it comes into a cell, it is the boss. It decides what happens. Whatever a cell normally does, when cytoplasmic calcium concentration goes up, the cell does whatever it does. So if that's a pancreas beta cell, it secretes insulin. If it's a neuron, it'll release a neurotransmitter. If it's a cardiac muscle cell, it'll contract, okay? So you need to know that. Calcium is the boss. It's like flipping on the light switch. It activates the cell, makes it do whatever it's going to do. You know, Mama, the boss, is the center of attention, controls everything. She is not reasonable. Whatever she says goes, and it is often not reasonable. It's just the way it is. So calcium is the aristocrat Mama. You need to know that. Okay, now here is potassium. Potassium's kind of like Dad, okay? But, you know, hard working, not around most of the time. He's out working. He's sort of the good middle-class guy who just makes sure stuff gets done. He makes sure the train is functioning, okay? He makes sure the roads are good. He makes sure whatever needs to be done, he gets it done, okay? That is potassium, the reliable middle class. Potassium is intracellular ion that makes the ion pumps work, the sodium-potassium ion pump, and it's going to do a lot of other things to make sure the cell is functioning the way it should. It's going to maintain the resting potential of, let's say, the cardiac muscle cell. Potassium is a good, hot, solid, reliable ion. It is your friend. You want more potassium. All right. The next ion to know about is magnesium. Magnesium is really partners with potassium in making the pumps run, making the ATP reactions run. But magnesium is more heroic. like Ben-Hur hanging on to the horses in the chariot races in ancient Rome in the movie Ben-Hur. Okay, magnesium hangs on to the second and third phosphates in ATP because that phosphate, it wants to break away that third phosphate. So here's the first, the second, and the third phosphate. That third phosphate wants to break away. Magnesium hangs on to it. It's got a double positive charge to hang on to those negative charge and does not let it be released until the enzyme reaction is ready for it to be released. Okay? So you have to have magnesium. Most Americans, they don't eat enough plants. Plants are the big source of potassium and magnesium, so they're deficient in potassium and magnesium, and that causes hypertension, and it also causes decreased cellular function. Okay, so you need to know magnesium is a hero. Magnesium is also a hero in another way. Magnesium is like a guard. Magnesium guards your NMDA receptor in your brain cell. So here's a postsynaptic neuron. Here's the NMDA receptor for glutamate, the excitatory neurotransmitter. And you can also remember M for magnesium, M for mellow. It mellows a person out. The reason it does that is magnesium is located right in the center of the NMDA receptor for glutamate, and it blocks calcium entry. So magnesium slows the neurons down from any abnormal function. So if you're low in magnesium, you might have anxiety, you might have insomnia, because you have overactive glutamate receptors, NMDA receptors that are calcium channels. So magnesium is your friend. Just like this guard is guarding his little fort here, he's got sentry duty. Magnesium sits there in the NMDA receptor and blocks it. So calcium cannot get through under normal conditions. Okay, where do you get magnesium from? You get it from plants. It's right there in the center of chlorophyll. Okay? That's why, by the way, I'm 61. I'm a low-fat vegan. I don't have any health problems. I can say all the patients have the same disease. They're all hypertensive. They're all pre-diabetic or diabetic, and those are the gateway diseases that lead to atherosclerosis. And atherosclerosis is just a blood clot. Okay. Now we're ready to get to the next step. Okay, we're talking a little more about the personality of these ions. Here is the personality of sodium. Sodium is the angry poor. Sodium is outside the city gates, and it's pissed off, and it wants to break through the gates and get into the city, busting into the city. Like Les Miserables, the angry poor, in Victor Hugo's magnificent novel, Les Miserables. Okay, and here is, these guys busting across the lines, okay, from this magnificent painting. The Hessian mercenaries in 1776, magnificent painting by Don Troiani, okay? All right, now here's how this stuff looks inside a cell. Again, you got your big concentration gradient. Potassium is high inside the cell. Everything is color-coded, by the way. Potassium is in blue, sodium is in red, calcium is in orange. Okay? So you got your baseline membrane potential being maintained by your sodium-potassium ATP pump. Net effect is to pump more sodium out. That also helps establish a negative resting membrane gradient. There's more to the resting membrane gradient than that, which I'll talk about in a moment, but that's part of it, the sodium-potassium ATP pump. We talked about how the establishment of a sodium gradient is coupled then to the knockout exchanger. It's also, the gradient is electrochemical. It's chemical in terms of the chemical gradient of sodium concentration. It's electrical in terms of the electro gradient by the negative resting membrane potential, whereby the positively charged sodium wants to get into the cell to get towards that negative charge. So that's the electrical component of the gradient. And this concentration difference is the chemical component of the gradient. So you have an electrochemical gradient. Okay, now we talked about the calcium being extraordinarily high outside the cell, so you always need ATP to pump something out. Okay. All right, so now this is sort of like what we were working towards. Here is the cardiac action potential in a ventricular muscle cell, like let's say left ventricle muscular cell. And the standard nomenclature for this action potential is this is phase 4. They don't usually include this little gap junction ion entry. I'm including it for the sake of our diagram, but you won't usually see this if you look in the cardiac physiology textbooks, okay? Then you have the 0 phase right here due to the fast sodium channels allowing a rapid entry of sodium. Okay, then you have overshoot where it goes above 0 in its number. Note that the resting membrane potential was negative 90. When the potential starts coming up, due to, let's say, it can be due to leaky sodium channels. It's also due to gap junction ion entry. When it gets above negative 70, that's sort of the threshold to fire your fast voltage-gated sodium channels, and you get a very rapid upstroke. Okay, you'll overshoot 0. That's called the overshoot. You get an early repolarization effect from potassium exiting, and then you run into what is called the plateau phase, where the amount of calcium entering the cell, which is the orange, is matched by the amount of potassium exiting the cell. I also want to show you why I think this action potential drawing is very helpful. Notice that it is color-coded. Blue, the resting membrane potential of -90, is about -90 because that's about the equilibrium potential for the potassium. An equilibrium potential means that if you have an ion, that ion will want to follow its chemical gradient. It likes to equalize its concentration gradient outside and inside the cell across the plasma membrane. The plasma membrane in a cardiac muscle cell is called the sarcolemma. Okay, so it wants to equalize its concentration gradient, but it also is also affected by the electrical gradient. So potassium, we talked about it, much higher inside the cell than outside the cell. So left on its own with just an open channel and no pump, it'll want to exit the cell. But it'll only exit the cell to such a concentration that its electrical component is also equilibrated. So you have something called the Nernst equation to determine the equilibrium potential for a given ion. At rest, the only channels that are significantly open are the potassium channels. Therefore, the resting membrane potential of a cardiac muscle cell is very close to the equilibrium potential for potassium. The equilibrium potential for potassium is about -94 millivolts. And because there's a tiny bit of like sodium leak as well, it's not a perfect 90, but the typical cardiac ventricular muscle cell is going to have about a -90 millivolt resting membrane potential. And it's very close to being that of the potassium, because essentially the only significantly open channel at rest in terms of leaky channels that spontaneously allow potassium to leak is going to be potassium leaking out. Nothing else major going on except for that. In the background, you're going to be running your sodium potassium ATP pumps, and you're going to be running your knockout exchangers just to clear up what came in with the last action potential, okay? All right, now this diagram right here shows below this black line is the cytoplasm. Above this black line is the extracellular matrix. So I'm showing you that the K plus is exiting the cell, and that explains phase 4, okay? I don't have anything down here for the gap junction. The gap junctions are let's say the pacemaker cell leading to all the other cardiac cells in serial form that are then going to cause an influx of positive charge to trigger the action potential, okay? All this red stuff here is the sodium entering the cell here, and that corresponds to the rapid upstroke here, okay? Then you got the blue right here, like the potassium exiting the cell, and that's the initial small partial repolarization. Then you hit the plateau phase. Notice that the orange line here is this calcium coming into the cell. These are the slow calcium channels, and they're also called L-type calcium channels for long-lasting calcium channels. They stay open longer, okay? And then the blue written at the same spot is the potassium that continues to exit. And they're in a plateau phase because you have an equal amount of potassium exiting and calcium entering. The abbreviation K plus for potassium means K for kalium, the Latin for that term. Okay, so this is the plateau phase. This was depolarization. Initially, the neuron is said to be polarized, meaning that instead of being at a 0 resting membrane potential, it's away from that. So it's polarized away from a 0 potential. And then when you depolarize it, you make it less polarized as you approach 0. And then when you go above 0, that's called an overshoot. Okay, so then when the membrane potential comes back down, you're repolarizing it, making it polarized again. Then you're back at resting membrane potential phase 4. Okay. The main thing happening during repolarization phase is potassium exit. Okay. The calcium channels will be closed at this time. And then we talked about resting membrane potential being about -90 millivolts, and that being primarily due to you have these leaky potassium channels that are open, allowing potassium to leak out. Okay, so this is how a cardiac muscle cell works. The influx of calcium is not that much in its overall amount, but what this is going to do, I'll discuss it in a separate lecture, but the calcium that enters during the plateau phase of the cardiac action potential is going to travel to the sarcoplasmic reticulum, which is really like the endoplasmic reticulum in a regular cell. And the sarcoplasmic reticulum is a huge reservoir storage site of calcium ions. And you're going to open up these channels that are called the Ryan-Odine channels. These Ryan like Irish names. Ryan's like an Irish name, Odine's like an Irish name, Odine's curse. Okay, but the Ryan-Odine calcium channels on the sarcoplasmic reticulum, they will bind to this calcium influx, and it will cause them to open, and they're going to release tons more calcium, and that's going to couple to, that's called excitation, is the action potential, contraction coupling, the actual contraction of the cardiac muscle. Okay, we'll talk about that in a separate lecture, but what do I think was useful from this lecture here? Number one, the idea of beginning with ocean water being the equivalent of the extracellular matrix. If you remember that, you'll always remember these ion things. And because you know the extracellular matrix is always high in sodium and always high in calcium, to pump those things out, you always need ATP. And it's always going to be high outside the cell. Always, always, always. And that can't change, because if you had more of that stuff inside the cell, you would raise the osmolality and the cell would burst. So life on Earth is not compatible with having more calcium and sodium sitting inside the cell. It just cannot be. And then you always have to pump it out, and you always have to pump against a high concentration gradient, so you always need ATP to pump it. All of these concepts are fundamental to understanding this physiology. And if you remember it this way, it'll be easy to remember. Remember those personalities. Sodium is the angry poor trying to bust into the city. The cell is like the city. So sodium is the angry poor trying to bust into the city. Potassium is the good guy, the hard-working middle class, just trying to maintain the ion gradient so the cell can function. If the cell doesn't lose its ion gradient severely, it just dies. Okay, so potassium keeps that cell alive. It's the friend of the cell. And then magnesium's the hero, literally hanging on to the ATP phosphates, literally blocking the NMDA receptor. It's the good guy. Okay, it's the heroic good guy. All right. Calcium is the aristocrat. It's like mama. Mama comes home and says, "What the hell is this? You didn't do the dishes? I told you to do the dishes. Why didn't you clean this up? Didn't you tell me you're going to clean this up?" And you got to do it. You know, you can't piss off mama. She's the boss, the aristocrat. So she makes the cell do whatever it needs to do. Okay. If you remember that about these ions, you'll find neurophysiology, cardiac physiology relatively easy to learn. So I hope that's helpful to you.